plaza, burning like the most noxious, poisonous things that we could imagine to try to increase air pollution levels in Berkeley, and we'd probably be successful. And furthermore, we could sort of randomly assign that, right? So we could say like, well, we're going to choose sort of every week we're going to flip a coin, and if the coin comes up heads, then we're going to build that huge bonfire and increase pollution levels. If it comes up tails, we won't, and then we'll collect data on hospitalizations and see how hospitalizations change as we randomly manipulate pollution levels. So in principle, you could do that, and if the pollutants weren't that expensive, it might not even be that costly to do. But I think there's something called the CPHS here, which is like Committee for the Protection of Human Subjects, that as a researcher you have to go through to get approval for your experiments, and I can guarantee you they would not approve that experiment. So ethical considerations, if not financial considerations, can basically prevent you from running the types of randomized controlled trials that you might want to have ideally. So instead, what we have to do is hope that we can get some sort of data in which this variable xi is as good as randomly assigned, in the sense that it's uncorrelated with other factors that could affect the outcome. Unfortunately, having this type of variation in x is not so common. So just running a plain regression of y on x is usually not going to give you a causal, not going to estimate a causal relationship. So you can run it and you can make descriptive or predictive statements, but you won't necessarily be able to give it a causal interpretation. So just to have another example, again, on the difference between description and causality, you can think about the relationship between mammograms and gender. So if you consider so mammograms are a somewhat controversial these days, I think, screening procedure for breast cancer. And so the controversy comes from the fact that it's not as easy as you might think to actually estimate whether or not they reduce deaths from breast cancer. So there's sort of like a cost side and a benefit side. On the cost side, first of all, there's a literally financial cost to doing cancer screening of pretty much any type that's not trivially expensive, and that's no different with mammograms. There's also sort of a clinical and psychic cost, though, which is that you can get lots of false positives. So like they might get a scan and then think that there might be very early stage cancer there. Then they have to go in and do a biopsy, which is itself costly and also can potentially be painful. And there's sort of a psychic cost of thinking you might have cancer when you don't. And since the rate of false positives is so high compared to the rate of actual positives, those costs can add up pretty quickly. So there's some controversy on how effective they are or at what age they should start being done. But you could sort of set something aside. You could consider a regression of a female dummy variable. So the outcome is whether or not you're female. Not that we would think that there are many things that can affect that outcome that we can manipulate. And we're going to consider a regression of that on whether or not the individual ever receives a mammogram. So again, if you ran that regression, the coefficient would be very large and very positive, since males essentially do not get mammograms. It's almost impossible for them to get breast cancer, although apparently not totally impossible. So when you ran this regression, what you would find is that those who, so you find a large positive coefficient that getting a mammogram predicts that you are in fact female. And so the descriptive interpretation would be those who get mammograms strongly tend to be female. There's no question about that. The predictive interpretation, which would also be valid, is that if we observe that an individual got a mammogram and we didn't happen to know his or her gender, we would predict that she is in fact female, and that again would be a good prediction. But then if we try to take the last step and assign a causal relationship or a causal interpretation to the regression coefficient, that's where things fall apart. So we'd say, well, if we give individual I a mammogram holding all the factors constant, then that will cause I to be female, and clearly that's not actually true. So one of these things is not like the other two, and unfortunately the causal interpretation is not something that we can often ascribe to regression coefficients. Okay, so one of the reasons why it's difficult to use these regression coefficients in order to make causal statements is that most outcomes are the result of lots of different factors. Most relationships, as we said at the beginning, are not deterministic. So y is partially determined by x, but it's also determined by a lot of other factors that are encapsulated in that e term over there. And if we actually observe some of those other factors that we think are affecting the outcome, then it can make sense to condition our expectation of y not just on a single variable x, but actually on all of these different variables. So we might observe, say, k variables that we think potentially affect or explain the outcome that we're interested in, and we'd like to condition our expectation not just on one of them, but on actually all k of them, so on x1 and x2, x3, so forth, all the way through xk. So we can do that. Originally we were just saying, let's look at how y changes as a single variable x changes, but now we're going to write down a conditional expectation that conditions y on this entire series of variables, x1, x2 through xk. And conceptually, this is similar to the more simple conditional expectation function that we wrote down at the beginning, but now we're just interested in how y is changing as a whole bunch of different variables change, right? So you can imagine changing x1, or you can imagine observing that x1 changes and seeing how y changes, and then also observing how x2 changes and seeing how y changes, and then observing how perhaps y changes when both x1 and x2 change simultaneously, and so forth. So there's two reasons why we might want to condition on a whole bunch of variables rather than just conditioning on a single x. One is that we might want to make better predictions of y. So it turns out that like linear regression, if you add in additional variables, it can never really make much worse predictions of y. So the reason is that what it's trying to do is it's basically trying to find the linear. So if we have, let me rewrite this now. So we're going to have multiple coefficients or multiple variables. So we have x1 and let's say x2, and now we have ei at the end there. So now let's say if we have two variables, there's sort of two possibilities. One is that both x1 and x2 have some explanatory power in like predicting y, and in that case the regression is going to estimate that both beta 1 and beta 2 are not equal to 0, that there's some positive or negative number. The other possibility is that x1 predicts y, let's say, but that x2 actually is totally uncorrelated with y and has no predictive power at all. The regression, I'll describe the multiple regression estimation procedure in a moment, but basically, since the regression is basically trying to come up with the best prediction of y, conditional on the values of x1 and x2, or basically trying to come up with like the best linear combination of x1 and x2 for predicting y. If x2 has no predictive power, then the regression is going to realize that, and it's going to say, well, since this variable is totally uncorrelated with y, there's no point in using it to try to predict y, so I'm going to set a regression coefficient of beta 2 equals 0, or beta 2 being very close to 0. And in that case, if that were the case, so if this were equal to 0, then basically this whole term drops out, and you're just going to have y is equal to beta naught plus beta 1 x1 plus ei, which gets you back to basically being in like the bivariate regression case where you just have a single right-hand side variable, right? So it turns out that sort of having more data on more variables can never really be that bad a thing, because in the worst case scenario, they're just not predictive, and the regression will realize that and like drop them out by assigning them coefficients of 0. And in the best case scenario, they might have predictive power, and then they'll sort of increase the power of your predictions. So one reason why we might want to run this regression is because we'll end up getting better predictions of y than if we just had a single x from that set of x's. But the other reason, which is I think usually is sort of more relevant to this class, is that what we may want to do is estimate the causal effect of some just one of those variables on y. So let's say we're interested in estimating the causal effect of x1 on y. So what we're really trying to do is get an unbiased estimate of that coefficient beta 1. But we think that there are other variables, x2 and maybe even x3 and x4 and so forth, that are correlated with x1. So if we just ran the simple regression of y on x1i plus EI. Essentially, these other variables like x2 and the rest are really just getting folded into EI here, right? So I'm just going to write this as, say, UI here, just so that I don't have the same thing in both of those equations. But you can see here that EI in this equation is actually equal to beta 2 x2i plus UI. And so the concern is essentially that x2i might be correlated with x1 or x1i. And if that's true, so x2i is being folded into EI here. If that's true, then when we see that x1i is high, we're seeing that y is high. But part of that is because beta 1 is non-zero. But part of it is also because when x1 is high, then x2 is high, and x2 is a determinant of y. It's in this EI thing. So there's, again, confounding going on, or what we call limited variables bias. So if the other variables are correlated with regressor of interest, these other x's are correlated with x1, then we'd like to basically condition on or control for the effects of these other variables. So to estimate the causal effect of x1 on y, we need to hold constant the other factors affecting y. And the easiest way to hold these factors constant, if we observe them, is just to include them in our regression model itself. So let's assume that the conditional expectation of y given x1, x2, all the way through xk is equal to a linear combination of these x's. So this is an assumption. I just want to be clear about that. When we were just talking about the simple regression case where you just have a y and an x, the conditional expectation function there might be nonlinear, and when we run a linear regression, we're assuming that we can at least approximate it with a linear function of x. In this case, again, y, or the expectation of y given x1, x2, all the way through xk, could actually be some complicated nonlinear function of all of those kx's. But for simplicity, we're going to assume that it can be at least approximated by this linear function of x1 through xk. So in that case, then we can basically write out the model as I did here, where y is equal to beta naught plus beta 1 x1 plus beta 2 x2, then plus EI or UI, some unobserved determinants of y that remain after you account for the effects of x1 and x2 and all the other x's that you have. So EI is again going to be or UI in that equation is going to be the deviation between our prediction of y and the actual value of y, just like it was in the simple regression case. And really nothing has changed relative to the simple linear regression, except that we now have multiple variables that we're using to predict y instead of just having a single variable x that we're using to predict y. So the downside of this, of course, is I can no longer show you a two-dimensional graph that's going to give you the function, the regression function, because we have to draw in like 3 or 4 or 5 dimensions. 3 dimensions would be a stretch given my drawing skills, and 4 dimensions, of course, would be impossible. So that being said, even though I can't sort of represent it for you graphically, the goal is the same as it was with the simple regression. Okay, so the goal is, again, to minimize the sum of squared deviations between our predictions of y and the actual value of y, so between our predictions and the actual data. The deviation between those two things is EI, and so minimizing the sum of squared deviations in this case means choosing the regression coefficients such that we're minimizing this sum of squares. So we're again just minimizing the sum of squares of the EI. So in this first part on the left-hand side of the equality, that's actually like the exact same thing that we wrote up with the simple regression. The only thing that's changed is now on the right-hand side of the equality, instead of having y minus the conditional expectation of y given x, so e of y given x, we now have y minus e of y given x1, x2, x3, and so forth through xk. So we're taking those deviations and then we're squaring them up, and we're of course going to substitute in for that conditional expectation function. We're going to substitute in that linear function of the x's that I wrote up, or that was on the slides earlier. So it turns out that if you solve this, so you can actually still solve this using calculus. You could sit down, take this function. So the first thing you want to do is we're trying to do is figure out, again, the optimal values of beta naught, beta 1, beta 2, and so forth, the beta k, that are going to minimize this sum of squared deviations. Because deviations are bad, we want our model to fit as well as possible. So the larger that sum of squares gets, so the worse your model is doing. So you could actually take this thing, differentiate it with respect to beta naught, set that equal to 0. That's one first order condition. Then you can differentiate it with respect to beta 1, set that equal to 0. That's a second first order condition. Keep on going. Eventually get to beta k, set that equal to 0. That would be your k plus 1 first order condition. And at that point, you're going to have k plus 1 equations, and you have k plus 1 parameters, so beta 1, beta naught, beta 1, beta 2, and so forth, beta k. And so you have just enough equations to solve for all of those different parameters, right? So you know that, like, in theory, you can do it. In practice, you could do it given enough time and like not making an algebraic mistake. But in practice, also, you could probably guess that like the equations are going to get more complicated, and you're going to need like several pieces of paper to actually write everything out. So it'll be a bigger pain. But the computer can do it for you just as easily as it could do the first one. So the intuition, so even though the formulas though are getting more complicated, the intuition is exactly the same as before. You're basically trying to choose these regression coefficients so that you produce the best fitting predictions of y, which is to say that on average your predictions of y get as close as possible, or actually the squared deviations between the prediction and the actual value of y is as close as possible. So by including these additional variables in the regression, we can essentially control for these variables. So to take it back to our original example, if y is hospitalizations and x1 is air pollution, and we want to estimate the relationship or estimate the causal effect of air pollution and hospitalizations, I gave a scenario where I said, well, one concern could be that temperature is basically correlated with air pollution. Hot days tend to have high levels of air pollution, and heat itself can also have, cause people to have heat stroke or heat exhaustion, which would then generate hospitalizations. So you could think, okay, well, one other variable then that I think is important in determining hospitalizations is temperature, let's say daily maximum temperature. So you could, of course, go and collect data on daily maximum temperature and put that in your data set, call it variable x2, and then estimate a multiple regression model where you are trying to basically estimate the relationship between air pollution, which is x1, and hospitalizations, which is y, while also controlling for the effect of daily maximum temperature, which is x2 in that multiple regression. So we're including temperature in the regression because we know that it and air pollution are correlated, and we're not going to be able to estimate this ceteris paribus effect of air pollution unless we can hold constant or control for the effect of temperature. So what this suggests is that the variables that we want to put into our model here, into our regression model, the additional x variables we want to put in, are basically the ones that affect the outcome and may be correlated with x1. So there's sort of two classes of variables then that we actually are not particularly concerned with putting in our model. So I'm just going to describe that and then basically we'll finish up. So the variables we're interested in are, as I said, the ones that affect the outcome and may be correlated with x1. So let's sort of think about variables that aren't that. So one possibility is that you have a variable that affects the outcome but is not correlated with x1. So in that case, you don't actually need to put it in the regression model. So even though like that variable might be an important determinant of the outcome, if it's not correlated with x1, then you don't run any risk that you're going to basically get a correlation between x1 and y that's due to that variable, right? Because the correlation, for that to happen, basically what would have to happen is that when x1 increases, then that variable also increases, and that variable has an effect on y. But we just said that x1 is uncorrelated with that variable, so when x1 increases on average, that variable won't change at all, and so it's not going to map through to an effect on y, even though the variable itself can have an effect on the outcome. So variables that aren't correlated with x1, we're not concerned about, and that's why the randomized control trial is so powerful, right? Because basically what the randomized control trial is saying is telling you or guaranteeing for you is that there are no other variables, even those that affect the outcome, they're correlated with your x, and therefore you don't need to actually include any other control variables in your regression. Now the other possibility is that you could have a variable that is correlated with x but does not affect the outcome. So again, you don't need to include that in the the regression either, right? So like you could think about having a randomized control trial where you assign people to treatment and control groups, and then you just have some other random bizarre variable that you decide to construct out of the treatment indicator. So it turns out that when you get assigned to the treatment group, not only do you get treated, but also we're going to like put your name on some weird list that nobody's ever going to see or something like that. So it couldn't possibly affect the outcome. Even though that variable would then be correlated with the treatment, it's not something you would need to include in the regression model because it's not something that is appearing in EI. It's just some other random factor. So those types of variables you don't need to worry about. But the things you do need to worry about are things that are correlated with treatment and affect the outcome.